Alright, so in this video I'm gonna be explaining another important paper with the title Linear Transformer Topological Masking with Graph Random Features. This iClear paper in 2025 is very important. When training transformers on graph structured data, incorporating information about underlying topology is crucial for good performance. Topological masking, a type of relative position encoding, achieves this by upweighting or downweighting attention depending on the relationship between the query and the keys in a graph. In this paper, we propose to parameterize topological masks as a learnable function of a weighted adjacency matrix. So it's a novel, flexible approach which incorporates a strong structural inductive bias. By approximating this mask with graph random features, we show how this can be made fully compatible with linear attention, preserving order of n time and space complexity with respect to the number of input tokens. Topological masking is simple when the attention is full rank. In this case, the entire attention matrix is materialized in memory, so its individual entries can be pointwise multiplied by a mask. But full rank attention famously incurs a quadratic space and time complexity cost, which may become prohibitive on large inputs. This has motivated a number of low-rank decompositions of A. To answer a question above, we propose to use graph random features. There are sparse randomized vectors whose dot product gives an unbiased estimate of an arbitrary function of a weighted adjacency matrix. So this is the schematic overview. The regular attention is order of n squared, where n is the number of input tokens. Topological masking modulates A by a function m of g, improving predictive performance. So it's modulating A by this mask graph function, by this graph function m. But the linear version, linear attention, there are more than 20 papers about linear complexity in transformers, like linformer, reformer, that use LSH, locally sensitive hashing. There are many approaches. Some of them are based on these random features that we have this transformation phi. And I will explain that paper in a different video. So this is a mask attention. We make this modification. And this K is just our attention weights. We have just with dot with M, with Hadamard product with M. Because M is a masking matrix, which is again n by n. N is the length of your sentence or sequence. But this mask could be either hard or soft. This is important. Topological masking is not just a mechanism to sparsify attention for efficiency gains. Its goal is to incorporate topological signal from underlying graph, improving predictive performance via a useful inductive bias. So we are improving the efficiency with low rank attention. So this equation 3, you see here, because we have as I said, we have a feature mapping, this kernel trick that we use. And this suggested low rank attention derives the speed from avoiding computing A explicitly, preferring to evaluate faster products like phi transpose V first and use them to weight the query feature. This makes the direct Hadamard product implementation in equation 2 impossible. If the matrix A is never explicitly materialized in memory, one cannot pointwise multiply each of its elements. So you can see graph node kernels as topological masks. So we intend M of G to quantify some sense of topological similarity. And we have talked about this diffusion many times. This is a linear combination of weighted adjacency matrix. And this is positive if and only if this holds. So it provides a very effective parametrization. Very quickly you can get your mask. So as I said, it's not just about sparsification. You want to encode some topological information. And this lemma is very important. And this is the proof of this lemma. So we want to reduce it to order of n instead of the quadratic, which is very bad. So our goal is now to replace phi by Monte Carlo estimates. And to build URF, one samples n random walks out of node v sub I. And P of omega is typically chosen so that walks randomly halt, prioritizing sampling lower powers of W that contribute more to the kernel. And this one here is just set of all walks between nodes v sub I and v sub q. And it has some good properties. These graph random features have some good properties. So you can visually summarize this paper in this picture, that you can see how these masks are created from random features, and then you use that mask and then you multiply it by A, adjacency matrix. This is how you compute the low rank attention with topological masking.